An introduction to ground penetrating radar (GPR) antenna. Ground penetrating radar (GPR) uses a propagating electromagnetic EM waves to detect changes in the shallow subsurface electromagnetic properties. The relative permittivity contrast between the background material and the target determines the propagation velocity of EM waves, which is the primary controlling factor in the generation of reflections, or the contrast between layers. When a field is placed on a material, its relative permittivity is known as its capacity to store and then permit the passage of EM energy. It can be measured in the lab or in situ. The transmitting antenna produces an EM pulse that travels into the subsurface and then bounces off an interface or scatters off point sources in a typical GPR unit. This reflected or scattered energy returns to the surface, where the receiving antenna records it. The travel time is the amount of time it takes for a wave to travel down to an interface and back up to the surface, and it is used to calculate the subsurface material's in situ propagation velocity. At or near sea level, the velocity of an EM wave in the Earth's atmosphere is 0.33 meter per second. Since the relative permittivity of all Earth materials is greater than that of air, the velocity of an EM wave propagating in all Earth materials would be slower than in air. Typical materials vary between 0.05 and 0.15. Since an EM wave's propagation velocity is determined by the material's relative permittivity, the amplitude and attenuation of a propagating wave are determined by the material's magnetic permeability and electrical conductivity. The tendency of a substance to become magnetized when an EM field is applied to it is known as magnetic permeability. Since amplitude attenuation increases as magnetic permeability increases, increased magnetic permeability results in poorer data quality and/or penetration depth. The propagation of EM waves is also influenced by electrical conductivity. EM signals are attenuated by materials with a high electrical conductivity. As a result, highly conductive materials can result in bad GPR data or a reduction in penetration depth. When a wave moving through the subsurface collides with an object that has different electromagnetic properties than the surrounding material, the part of the wave that reaches the object changes direction, which is known as scattering. Spectral reflection scattering, diffraction scattering, resonance scattering, and refraction scattering are the four primary forms of scattering. The basic concept of spectral reflection at a horizontal interface as shown in Figure 2. The primary form of scattering targeted in most surveys is spectral reflection scattering, which is defined below. The angle of incidence equals the angle of reflection in spectral reflection scattering. Any energy can refract through the interface into the underlying medium rather than reflecting from the interface. This energy will then flow downward until it comes into contact with a different electromagnetic interface layer. Some energy will bounce off the second interface and return to the surface, while other energy will refract down into the third medium. As the downgoing EM waves encounter each interface in this multiple interface situation, there will be multiple reflections in the GPR result. Nearly all GPR practitioners have access to the basic information described in the preceding summary. The essential variables, parameters, and theory equation that govern how EM waves behave and respond to changes in subsurface electromagnetic properties are detailed below. Physical basis. Maxwell equation. Maxwell equations are important for understanding GPR behavior since the relationship between material, electromagnetic properties, and EM wave propagation can be quantitatively described. E is the electric field strength vector, B is the magnetic flux density vector, D is the electric displacement vector, H is the magnetic field intensity, Q is the electric charge density, and J is the electric current density vector in Maxwell's equation. Shay is a good guide for readers unfamiliar with the various notations in vector calculus. Electric currents produce magnetic fields and vice versa, according to Maxwell equations. Magnetic fields are form closed loops, while electric fields may form closed loops or pre-charges. The electric and magnetic physical properties must be understood in order to understand GPR wave propagation. The material constants of relative permittivity, magnetic permeability, and conductivity, as defined in the introduction, are the most important variables in GPR. Equations and 5 and 6 and describe the relationship between relative permittivity and magnetic permeability and the so-called dielectric constant and index of refraction. Permittivity. Permittivity principles in general necessitate a discussion of what are known as dielectric materials. The majority of natural earth materials are dielectric materials, which are electrical insulators. If a material satisfies the following equation, it is said to be dielectric, where W denotes the angular frequency in radians per second and O denotes the electrical conductivity of the materials in Siemens per meter. In the same way as elastic materials bend and store potential energy in response to external kinetic energy, dielectric materials store energy in response to an external electric field. The ability of a substance to polarize, endorse polarization, and store energy in response to an external electric field is referred to as permittivity. Where an external EM field is applied to a substance, the atoms undergo molecular orientation, also known as interfacial polarization. The charges separate until an internal EM field balances out the external field, resulting in net energy storage. However, it's worth noting that the process is complicated by the fact that charge movement causes energy loss or dissipation through heat. Permittivity is expressed as a complex number with both a storage and a dissipation. These two elements are 90 degrees out of phase with each other. The real part of permittivity is a measure of polarization and energy storage in a material that can be represented by the actual component of the permittivity usually has values ranging from 8.9 times 10 raised to negative 12 to 7.2 times 10 raised to negative 1. The imaginary component is a measure of material's energy, dissipation, or loss, disconnected to the material's electric conductivity. Conductivity. The electrical conductivity is a measure of the ease of electron movement within a material that is under the influence of an external electrical field. Electrical current can propagate through rock and minerals via three methods of conduction. Electrolytic conduction is the dominant process in moist or wet material. Electrolytic conduction is dependent upon porosity and the conductivity of the pore fluid as shown by Archie's law. The concentration of total dissolved solids can also influence the electrical conductivity of groundwater, as shown in McNeil's approximation. EM wave propagation. Electromagnetic waves can be generated by a variety of methods such as discharging spark or by an oscillating molecular dipole. Visible light is a commonly studied form of electromagnetic radiation and exhibits oscillating electric and magnetic fields whose amplitudes and directions are represented by vectors that undulate in phase as sinusoidal waves into mutually perpendicular planes. The magnetic field oscillates perpendicular to the electric field at the same frequency. The electric and magnetic vectors are perpendicular to each other and to the wave propagation direction, representing the amplitude and vibration directions of the waves. For most materials that occur in living cells, the magnetic permeability is equal to a value of unity, so that this is the formula for magnetic permeability. Empirically, the velocity of light is known to be inversely proportional to the refractive index of the material through which it propagates. The vector describing the interaction between an electromagnetic field and a substance lies in the same direction as the electric vector. Typical GPR assumptions. Three-dimensional electromagnetic waves exist. However, for the majority of GPR applications, EM waves are assumed to propagate in two dimensions based on the assumption that measurement of the third dimension is unnecessary when using reciprocal antennas, as EM waves propagate through strongly anisotropic materials. However, this is invalid. GPR signal analysis is often restricted to EM waves operating in the frequency range where displacement currents predominate and transmitted frequencies surpass the material's transition frequency instead of induction in a substance. These conditions because EM waves to propagate in materials with high magnetic permeability. This statement is usually false. The majority of Earth materials used in GPR studies are dielectric and lossless or low loss. As previously stated, these conditions are crucial for the generation of EM waves that propagate and oscillate for any acceptable numbers of cycles. If these assumptions are violated, using GPR as a reflection imaging technique is impractical or impossible. Antennas and polarization. Near-surface geophysics and electric and wave polarization are two forms of polarization that are widely discussed in the literature. The bound charges of a dielectric material orient or align themselves in the direction of the applied field for electric polarization. The four basic characteristics of a propagating EM wave are amplitude, frequency, phase, and wave polarization. Three concepts are general, significant, and often confusing when discussing wave polarization of GPR signals. First one is polarization due to antenna construction. The second one, polarization due to antenna orientation. And the third one, depolarization or polarization changes due to target orientation are the three terms. Antenna polarization. GPR antennas typically consist of monostatic or bistatic horizontal center, fed half-wave dipole antennas. Monostatic antennas use a single antenna as both the transmitter and receiver. Most commercially available GPR antennas generate linearly polarized EM waves. Polarization due to antenna orientation is determined by the location of E and H relative to the vertical plane of incidence. For GPR devices that use center-fed half-wave dipole antennas, oriented parallel to the long axis of the antennas and is oriented perpendicular to the long axis.